See.
Okay, so we can continue. Our second speaker is Riccardo Penco, talking about the naturalness of vanishing black hole response. Please.
Perfect. Thank you very much. So first of all, I would like to start by thanking the organizer for inviting me to give this talk. This is my first time here at GGI, and so far it's been really cool, both colloquially as well as thermodynamically speaking. So if I had been a lawyer, my title would have been more something like this. What I will focus on for this talk is going to be black hole response in the linear regime. I will mostly talk about static response, and except for a few comments, also I will care mostly about conservative response. And the work I'll discuss today was done in collaboration with Lam Hui at Columbia, Austin Joyce at the University of Chicago, Lucas Antoni, who recently moved from ICTP to APC Paris, and Adam Solomon at McMaster University. Okay. Now, since I'm gonna talk about linear response, I thought I'd start by saying just a few words about an example that probably all of us have seen at some point in our career. This is sort of the poster child for linear response, namely a situation where you have a dielectric field, a dielectric sphere in a constant external electric field. This is such a classic problem that, in fact, I stole this picture from Jackson. Strictly speaking, the exact problem here is very nonlinear in the interior of the dielectric. But for small enough amplitudes of the electric field, we can assume that the response, namely the polarization density inside the sphere, is linear in the electric field. And under this assumption, so what we do is we introduce a dielectric constant that tells us the proportionality essentially between polarization, if you want, and encodes the relation between polarization and electric field. And then we can solve this problem exactly. By that I mean solve the Laplace equation everywhere, assuming that the potential remains constant at the origin. And our solution outside the sphere takes this form, where there is a growing piece in R that is simply what is needed to recover at very large distances the constant electric field that we placed our sphere in. And there is the K part, which in this case is a dipole type of field, and it encodes the response of our sphere. And essentially, this is the part of the potential that is due to the fact that our sphere got polarized. Now, the little p here is the induced dipole, and its magnitude, of course, depends on the strength of the external electric field. But what is a characteristic property of our object is actually the ratio between the two, which is what we call the susceptibility. And as you can see, in this case, first of all, it depends on the microscopic details of your object, and up to factors that typically are of order 1. The susceptibility is determined by the only length scale that you have in the problem, namely the radius of your sphere. So what I'll do for the rest of this talk is essentially take this sphere and replace it with a black hole, take this external electric field and drop the assumption that it is uniform. I will consider fields that can vary in space, they're inhomogeneous. And in fact, I won't restrict myself to just electric fields. I will consider all sorts of fields, gravitational, scalar, magnetic fields, all kinds of fields you want. Okay? And if I'm interested in what goes on outside the black hole, now the exact problem, for example, in the case of external gravitational fields, is nonlinear due to the very nature of GR. But once again, if we restrict ourselves to fields that have a small amplitude, we can work in perturbation theory and just linearize Einstein's equations. And so just study essentially the dynamics of perturbations around the black hole. And the advantage of doing that is that now we can describe these perturbations for any type of fields, so fields with any spin, and we can decompose this field in angular momentum numbers, L and M, and for all these quantum modes, quantum numbers, perturbations are described by the Tucholsky equation. And when I say I'm interested in the static response, I'm going to focus in particular on the Tucholsky equation in the zero frequency regime. Okay. So we can play exactly the same game we played for the dielectric sphere. And now the interesting boundary conditions that we want to impose are the requirement that our perturbations suitably defined remain finite at the horizon, whereas the asymptotics at infinity are a bit more complicated now than compared to the sphere. For angular momentum L, our modes will grow at most like R to the L, and then we're going to have subleading powers until eventually we reach 1 over R to the L plus 1. And in analogy with what we did for the electric sphere now, these the coefficient of this follows here will interpret it as being due to the induced multiple. And so the susceptibility is going to be just the ratio between the coefficient of this growing power and the coefficient of this subleading power. And in general, because we're working in Fourier space and in L&M space, this susceptibility does not have to be real. In general, it's a complex number. And the real part describes what we call the conservative part of the response, whereas the imaginary part encodes the dissipative part of the response. And interestingly, so if you play this exercise for a black hole, you might expect to get a real part of the response that, again, is determined by the only length scale that you have in the problem, the Schwarzschild radius or the horizon radius. But in fact, you find that it is exactly 0 for fields of any spin, for any L, and for any M. A few comments. So if we, all I said is valid in general for a Kerr black hole. If we set the black hole spin to 0, then also the dissipative part of the response in general will vanish for any L, S, and M. For S equal 2, this what I define as the conservative part of the susceptibility is more usually known as log numbers. Now you have different numbers for any L and M. And this chi prime really vanishes for all L and M only in 4 dimensions and in general relativity. If you consider departures from GR, or if you go to higher dimensions, then in general, some of your chi prime won't vanish. And one last comment is that there's been a little bit of confusion when it comes to the response of Kerr black holes, mostly due to the fact that at omega equals 0, the dissipative part of the response is non-zero. And I would say this was perhaps the main part of the main reason for the confusion. But you can understand this. Well, so typically, say for a dielectric sphere, chi double prime would be non-zero at finite frequencies, whereas for a black hole it is non-zero also at 0 frequencies. But you can understand that by going in the reference frame of the black hole and realizing that if you have a perturbation that is modulated in space, in the rest frame of the black hole, this appears as a modulation in time. Okay? And in fact, chi double prime is precisely proportional to the spin of the black hole, which is the frequency at which this field would vary over time. Okay? Now, this is quite a remarkable property. Okay? As far as I know, black holes in 4 dimensions are the only objects in nature for which the conservative response, linear response, is 0 for any field for any multiple. This result has, is very interesting, first and foremost for observational reasons, because it gives us a clear target. For any other object, typically the response is stuff of order 1 times the typical scale of your object, let's say the radius. Right? And so there is a clear gap between the value of chi prime for, say, a neutron star or a black hole. Right? And so this makes it particularly appealing from an observational viewpoint. From my perspective, I mostly got interested in this result because it seems to pose a naturalness problem at very long length scales, and not as severe as the cosmological constant problem, but the hope was that by trying to understand this result better, we can actually learn something new about other naturalness problems in high energy physics. Okay? So what I'd like to do is explain first why this result is somewhat puzzling. And to do that, let's look not just at a black hole, but say at any object. If we look at it from very, very far away, at length scales much larger than their size, then at a first pass, we can approximate it, or we can describe it using a point particle action. And this action is supposed to contain an infinite number of terms. So usually we would truncate our action here, but in fact, if our object has a finite size, there is going to be an infinite number of operators that will describe, for example, in this case, I'm considering interactions between an object and an external electromagnetic field. Okay? If I wanted to consider interactions with an external scalar field, then I would have higher and higher order operators that depend on phi and their derivatives, and its derivatives. Okay? Now, this infinite tower of terms in the Ward-line action is organized in a derivative expansion. So more and more derivatives are suppressed by powers of the size of the object times the, or divided, if you want, by the wavelength of your external fields. And time derivatives also would involve a characteristical speed, which could be the speed of light for black holes. It could be the speed of sound inside your material if you have a ball of iron. And it is this type of derivative expansion that ensures that even though your action would contain technically an infinite number of terms, at any given precision, you can just focus on a few of these terms. Now, all these operators actually are there to encode the physics of all the physics of your object. And in particular, one thing that they encode is the response, both linear, but in particular, both non-linear, but in particular linear. Right? And so to show that, let me focus on an even simpler case here. Let me just consider an object that is neutral. So this term is not there. And I'm gonna work in the rest frame of my object so that I have zero velocity. And now imagine turning on an external constant electric field like we did in the first slide. Okay? Then I could evaluate my Lagrangian, and what I would find is that it takes some constant value, V0, which now is not just the rest mass of the object, because our object is also somewhat polarized by the external field. Polarizing an object costs some energy, and so this V0 also includes that energy that that corresponds to the polarization. Okay. And now let me tweak my external electric field a little bit, change it from E0 to E0 plus delta E. Okay. And at first order, I expect this rest energy of my object to change by an amount equal to the potential energy of a dipole in an external electric field delta E. Okay. Which means that if I plug E naught plus delta E in my action and expand up to linear order in delta E, whatever sits in front of delta E, I should interpret it as being the dipole that was induced by the field E naught. So if we do that for the previous action that I showed you before, we find that this induced dipole depends on the various coefficients in our effective action. For example, for a constant field, on the coefficients that I call C1 and C2. And so this induced dipole is proportional now to my external field. And the proportionality constant is what I defined to be the susceptibility earlier. Okay? And so this shows there is a clear relation between the susceptibility that encodes the linear response and the various coefficients in our point particle effective action. By the way, if there are any questions, feel free to stop me at any time. At this stage, yes. If there was one, then I would need to supplement my action by adding a coupling with this fixed dipole moment. Yes. Yeah, thank you. Very good. So now I could, by the way, play the same exercise with a constant external magnetic field rather than electric field. What I would find now is a magnetic susceptibility, which would be a different linear combination of C1 and C2. And demanding that the response is 0 in both cases means that both C1 and C2 should be 0 in my action. But I could also place my object in an external field that is not just constant, that varies over space, and play the same exercise. And what I would find then is that there is an infinite number of couplings in my effective action that needs to be exactly 0 for a black hole. Okay? And whenever we have an effective theory in which an infinite number of operators is just missing, it's because there is a symmetry, an underlying symmetry that prevents them from being there. Okay? And so this suggests that perhaps black holes should be, in a sense, more symmetric compared to other objects. And this observation has spurred recent activity in looking for hidden symmetries of black hole perturbations. And there are particularly two types of hidden symmetries that have been discussed in the literature related to, in the context of love numbers over the last couple of years. One said due to our group, another one due to a group at NYU. So what I would like to do next is try to discuss these symmetries in the simplest possible context, just for the sake of time, which is that of a scalar field, a scalar perturbation of a Schwarzschild black hole. And then I will tell you which ones of our results, in fact, most of them, but which results exactly extend to more general setups, other fields, and care. Okay? And ultimately, I will be interested in the static response, because it's only in that limit that the conservative response vanishes. But for now, what I will do is just focus on a slightly larger subset of frequencies. So I will work at small but finite frequencies. The idea being that in this limit, I can also still say something about the static response. But the advantage of doing that is that it will allow me to sort of discuss in the same framework both the symmetry that we found and the ones that the NYU group found. Now, when we work at small frequencies, and by that I mean 1 over omega much larger than the Schwarzschild radius, the region outside the black hole can be split in a parametrically large near zone and a far zone. And what I will focus on is this near zone, because in the static limit, 1 over omega goes to infinity. And so any statement that I can make and is valid in the near zone, it's going to become an exact statement for the static problem. In this near zone, I can take my previous action for a scalar on Schwarzschild and approximate the kinetic term by replacing r to the 4th over rs to the 4th. Now, this is a procedure that almost every paper agrees on. It's not necessarily a super systematic procedure, but you can argue that it is clearly a good approximation near RS, and where it becomes a bad approximation near 1 over omega. In this region, other parts in the action are much larger than this one, so you're making an error on a term that is subdominant, and so you can get away with it. So with this approximation, we are changing now, we are changing, yes? That's right. So if we're interested in a radiation problem, we're actually looking at that right now. You can do a matching between two different approximations. One in flat space, valid for R much larger than RS, and one in the near zone. And these two regimes have an overlap. You can match in between the two, and then you can discuss radiation. Yes. Yeah, but for today, I'll just focus on static response mostly. So after you perform the previous approximation in the action, you can ask now, this action, does it correspond to a minimally coupled scalar on some other effective metric? If so, what is this effective metric? The answer is yes. This is the effective metric that would correspond to the action with the near zone approximation. It's really a sum of two pieces. One that is just a metric on a sphere with constant radius, and the other one that in some funny coordinates just corresponds to some portion of two-dimensional anti-de Sitter. Now, this metric has also some nice properties, namely, well, the fact that it's ADS2 cross F2 means that now we have 6 Killing vectors rather than just the 4 of Schwarzschild. So in this near zone, we've grown some approximate symmetries. But more than that, it is a conformally flat metric, which means that we also have 9 additional conformal Killing vectors. And because the Ricci scalar of this metric is also 0, it means that phi is conformally coupled to our metric, and therefore that our action for a scalar actually has 6 plus 9, 15 symmetries now. Okay. And this 15 symmetry put all together just satisfy the algebra of the conformal group in 4 dimensions. And they are just the 3 rotations that also Schwarzschild has, the 3 ADS2 isometries, and again, these 9 conformal Killing vectors. Now, within this framework, it becomes clear what our symmetries look like and what the NYU symmetries look like. The NYU symmetries are just the isometries of ADS2, which in fact are equivalent to SL2R group at the level of the algebra. Whereas the symmetries we focused on are the subgroup of the conformal group that is basically like the Lorentz group, if you want. So correspond to the 3 isometry plus 3 of the conformal Killing vectors. Okay. So are clearly different subgroups of these large 4-dimensional conformal group. So I'll be happy to tell you more about these later if you want. But for the rest of the talk, yes. Well, they're very explicit once you go to the near zone, but if you consider the exact problem of a scalar on Schwarzschild, yeah, well, so that's right, but I guess we call them hidden because if you start with the problem on Schwarzschild and you look at the static response, you wouldn't necessarily immediately realize that there are these underlying symmetries. It's only once you make this intermediate step of going to the near zone that you realize that actually the effective metric is much more symmetric. Yeah. That's right. No, so that's right. So I think the one that you have in mind is probably what is valid for extremal black holes. Whereas here, what I'm discussing is a different limit. This approximation is valid even just for Schwarzschild, or it's also valid for Kerr in the non-extremal limit. So it's a different, but in the literature, there are many ADS2s that appear, many SL2Rs, for example, in the context of the Kerr CFT correspondence. And all of these symmetries correspond to slightly different approximations in slightly different contexts, so it gets confusing, but yeah. No. No. So I think this is related to his question. Our approximation is actually valid also for R large compared to RS, provided omega R is much smaller than 1. That's right, but because what we're approximating is not the metric, okay? So in the near horizon limit, yeah, sure. In the near horizon limit, what you do is you, in the extremal case, you really look at the geometry and you take a particular scaling limit and you just approximate the geometry. Yes, sorry, can I just finish the thought? So here the situation is different. I cannot define the limit that I took without also talking about a field that lives on Schwarzschild. Right? So the frequency of the modes that I look at play a crucial role in determining what is the range of validity of my approximation. Whereas for the usual near horizon limit, you can define that without any reference to any other field. Okay. That's right. Well, so my claim is that if you solve the scalar equations on top of this metric, the solutions that you get are going to look very much like the solution you will get in Schwarzschild, provided the modes provided you're looking at these solutions in the near zone. As soon as you go at very large R, so larger than 1 over omega, then the solutions on top of this metric will look very different from the solutions on top of Schwarzschild. Yes. Well, I want a master scalar. Well, let's see. Yeah, so I focus on the master scalar eventually because I'm interested in looking at the response at infinity and having these different fall-offs that grow and decay as powers of R. Off the top of my head, I don't remember if the same is true for, yeah, probably it's not. Yeah. Yeah, that's right. Yeah. Okay, how am I doing with time, by the way? 25. Ah, fantastic. Okay. Perfect. Okay, so where were we? Very good. So as I said, the SO3,1 subgroup. You said 25. Sorry, too late. So the SO3,1 subgroup that I would like to focus on is made of rotations and these 3 Killing vectors that look like so. And I'm not showing them because they are particularly memorable. But mostly the point that I want to drive home is that there is absolutely no time dependence here. Okay? There are no components in the time direction of the scaling vectors, and there is no explicit time dependence in the components of these vectors. Okay? Which means these are actually exact symmetries of the static sector. So I could have derived them by just taking the action for a scalar on Schwarzschild, restricting my attention to modes with zero frequency, and then asking what are the symmetries of this action. And I would have found that that static sector action would be invariant under all these symmetries. Okay? You can understand this also after some theory definitions as the statement that a static scalar on Schwarzschild essentially lives on a three-dimensional hyperbolic space, which is a maximally symmetric space with 6 scaling vectors. And so in this language, these symmetries are the 6 scaling vectors of the hyperbolic space. For the purposes of explaining the absence of static response of black holes, I could have just done that. The reason why I introduced this intermediate step of the near zone approximation was just to make content and look at, in the same framework, at both our symmetries as well as the ones that were discovered by this different group. Sorry. Okay, very good. So now what I would like to do is use these symmetries to argue that for a black hole, the response should be 0. And what I will use is the fact that these symmetries admit a regular flat limit. So if I take the previous scaling vector and I let Rs goes to 0, I find that they have a finite limit. And if I go from spherical coordinates to Cartesian coordinates in 3D, what I would find is that the 3 conformal Killing vectors really give rise to spatial conformal transformations of a 3D scalar. And so the claim is this symmetry should also be a symmetry of the flat space action, which is, if you want, also of the action where we treat our black hole as a point particle in flat space. And you can check now. You take this action, you can check whether these terms that are localized on the world line that would give rise to the static response for L equal 1, L equal 2, and so on. You can check whether these operators are in fact invariant under this symmetry. And it turns out that they are not. Which means their coefficients must be 0. They cannot be there for black holes because the action for black holes should have this symmetry. And by the way, the way we checked that these terms are not invariant is just by running the standard Noether argument to derive the Noether current. And what we found is that now the current that would be associated with this symmetry is no longer conserved. And the conservation of this current is broken precisely by terms proportional to lambda 2, lambda 4, and so on. Okay. Yes, Peter. Okay. Yes. Yes. That's my next point. Perfect timing. So the difference in the study is the following. So what I found here is an exact symmetry of a scalar on Schwarzschild in the static limit. Okay. Now, for a black hole, Schwarzschild is valid all the way down to the horizon. Okay? And as long as, and so everywhere outside the black hole, my symmetry is valid. For a star, due to Birkhoff's theorem, the metric is still Schwarzschild all the way up to the surface of the star. at which point the metric changes. And there, it is no longer true that the effective metric felt by a scalar has these symmetries. And so these symmetries are broken at a scale r of order of the radius of your star. And like in any other effective theory, whenever you have a symmetry that is explicitly broken at a certain scale, the coefficients of the operators that would be set to 0 by that symmetry acquire a natural scale which is of order of the symmetry breaking scale. Yes. Mm-hmm. Okay. Yes. Sure. And you would say, well, that's it. Yeah. I guess. But in the black hole, hard to deal with it. There's a scale. I don't understand where you just know. Yeah. That's right. Very good. So at the point particle level, you can't talk anymore about boundary conditions at the horizon. You've lost that information, right? What do you mean by that? I suppose, but I think I'm not sure this is going in the direction that Vittorio suggested. So I think to answer your question, we need to go back to the actual geometry. So let's take, like you said, let's take a black hole. And now we know that for a black hole, we would impose at the horizon ingoing boundary conditions at finite frequencies. In the static limit, we would just take the omega goes to 0 limit of those infalling boundary conditions. And now let's take that solution and extrapolate it to 3GM. Okay? It's going to determine some solution. And I could, if I wanted to, impose that as my boundary condition at 3GM. That's what you're suggesting, right? Very good. So the claim is that the solutions that are purely infalling in the static sense at the horizon actually are invariant under the symmetries. And therefore, when you go to the point particle limit, your action should still be invariant under the symmetries. If those solutions were not invariant, then what you would have would be spontaneous symmetry breaking. And in that case, when you go in the deep IR, you don't see that symmetry anymore. Okay. Yeah. Yes, that's right. Exactly, because very good, and maybe that's a better way, even better way of answering the your question. Okay, for a star, right? The way we would solve the problem is now, like for the dielectric, we would impose regularity at the origin, and then extrapolate all the way to the surface. Now we would have a mixture of ingoing and outgoing modes, and now that solution would no longer be invariant under these symmetries. Okay, so that's right. Yeah. So this is going to become more clear, I think, in the coming slides, where I look actually at how this symmetry argument plays out in the UV. So when I really work on top of my background metric as opposed to in the point particle limit. The reason why I made this detour is because the naturalness problem that I introduced at the beginning is really a problem in the point particle limit. Okay? It's not a problem on Schwarzschild. Because on Schwarzschild, you do the calculation, you solve the Kolsky equation, and you get what you get. Okay? The puzzle is really in the IR, in the effective theory. And so if you want to claim that you have a symmetry resolution to the problem, you need to have an argument that works at this level, okay? But of course, we also have a symmetry in the UV, and so we can use it to derive the vanishing of log numbers or of any response purely from symmetry arguments without actually solving the full equation for perturbations. Okay? So maybe let me go over the next two slides. If they don't answer your question, we can go back. Okay. Okay, so how do these SO 3,1 symmetries look like in the static sector? If you're really trying to solve an equation for the scalar on Schwarzschild, right? Then the equation for a scalar or for the Lth mode of a scalar would look something like so, where I have this operator where delta is r times r minus rs. Okay? And in angular momentum space, these conformal Killing vectors will actually mix modes with different L. And will mix mode with different L with some first order differential operators that I call d plus and d minus here. So their form is not particularly illuminating, but what's more interesting is the algebra that they satisfy together with the differential operator that appears in your equation for the scalar. Because of this algebra, you can show that if you take a mode, a solution with angular momentum L, and you act on it with a differential operator d plus, you'll get another solution with angular momentum L plus 1. And similarly, with d minus, you can get a solution with one less unit of angular momentum. So they work something like raising and lowering operators now, where you're raising the angular momentum number. Okay. And you can also use this d plus and d minus to define an additional set of symmetries that now are symmetries of any sector with fixed L. Right? The construction would look like so. For L equals 0, you can show that this is a symmetry. And then you can build higher QLs just by by recursion, by sandwiching QL minus 1 in between a D plus and a D minus. Okay. And so you can show that operators QL built like so actually commute with your differential operator HL. Now, pictorially, it's a little simpler to see what's going on. At any given value of L, we have two independent solutions because our equation is second order in R. And the QL symmetries work at a fixed L and interchange the two independent solutions, whereas the D plus and D minus takes us from a solution with L minus 1 to one with L to one with L plus 1, and so on. And so we had this ladder-like structure of symmetries when we work in angular momentum space that are associated with the conformal Killing vectors that I showed before. Yes, 5 minutes, perfect. And using these symmetries now at any fixed L, we can run a symmetry argument to show that the response should be 0 without actually solving exactly the solutions for the scalar. And the argument goes as follows. Because the QLs are a symmetry, there is going to be some conserved current associated with this symmetry. And in the static limit, because we went also to angular momentum space, conservation of current is really just a statement that the radial derivative of the radial component of the current vanishes, which means the radial component of the current, which in terms of phi and all these operators really looks like so, this is supposed to be a constant everywhere outside the black hole. Okay. And so what we can do is look at our solutions, at the asymptotic form of our solutions, close to the horizon or at infinity. Our two independent solutions at infinity we've seen before are either growing modes like R to the L or decaying modes. And our two independent solutions close to the horizon, one of them goes to a constant, which is the one that we actually care about when it comes to solving and finding the static response, whereas the other one typically blows up. Okay? And if you want the mystery about the vanishing of love numbers or response of black holes, is that typically when you pick one of the two independent solutions on one side of your region of space and you extrapolate all the way to the other side, you would find an admixture of the two independent solutions, which means you would also find some non-trivial fall-off, some non-trivial response. Whereas the absence of response is the statement that if you start with a constant here, you really only get one independent solution on the other side. Okay? And now we can understand this from the conservation of current, because we can go close to the horizon and evaluate this current and find that it vanishes for the solution that is a constant, and it's non-zero for the solution that diverges. Okay? And similarly, at infinity, the current is non-zero if you have a non-trivial decaying fall-off, but it's zero if you only have a growing mode. Okay? And so if you start here with a constant, conservation of current tells you that JL should be zero everywhere, which means that by the time you reach infinity, you can only have a growing mode. And so you have zero response. Yes. So I call this UV because here my space in between RS at infinity is really Schwarzschild. I'm no longer in the limit where I am at scale so much larger than Schwarzschild that I can work in the flat limit and treat my black hole as a point particle. Yeah. Okay. Very good. So this is a symmetry argument now on Schwarzschild that leverages the symmetries to show that there should be zero response. And just a few comments to conclude. The exact same story works for a scalar on Kerr rather than Schwarzschild, with the only difference that the current now would not be exactly zero for the solution that we care about, but would be actually equal to the dissipative response squared for reasons that we don't fully understand, but we're actually very interested in understanding better. We could also generalize these to fields that are, say, spin 1 or spin 2. Okay, and the same would go through. You can show that our symmetries are also symmetries of the Tokowski equation in the static limit. And in fact, perhaps in this afternoon's talk, we'll hear more about this very nice paper that shows that if you look at the Tokowski equation, not just in the static limit, but in the near zone, and you look at the Tokowski equation for ADS2 cross S2, these two look exactly the same. Okay. Okay, there's also a laddering spin that I won't have time to discuss. And finally, it's just a curiosity, but it actually played a big role in us, in our understanding. There is a very similar result for odd-dimensional. Sorry, this should be the sitter, I think, not anti-de Sitter. That is called transparency. So if you start in the very far past with a purely outgoing wave, and you look in the very far future, if you are in odd-dimensional de Sitter, you find that once again in the far future you only have an outgoing wave. You don't have that mixture of the two waves. This is a very similar situation to what happened here for black holes. Okay, so just to conclude, what I showed you, what I discussed are some hidden symmetries that become manifest in the near zone. And we can understand, we can learn something more about this by working in angular momentum space, where they essentially morph into a ladder structure of symmetries. We find this to be a convincing argument or symmetry explanation for the vanishing of black hole response. But this is not to say that there isn't more work to be done. And a few of the things that we would like to do in the future are listed here. Be happy to tell you more about any of these, but maybe since I'm probably over time, I should stop here and just thank you for your attention.
Thank you. Are there any questions? Yeah. Do you want?
Yes. Very good. So, I think it's easier to see what changes in terms of this ladder structure of symmetry. So in 5 dimensions or in higher dimensions in general, as you may know, the difference is that not all love numbers, say, or response coefficients vanish, only those for which L over D minus 3 is an integer, okay? Where D is a number of space-time dimensions. So in D equal 4, this is always an integer, and everything vanishes. In higher dimensions, only a subset of L have vanishing response. And you can show that these ladder symmetries essentially make you jump from only in between values values of L for which these are integers. Okay, and so you can only make a statement about the vanishing response for these particular values. Yeah. Yes, so you have more M's. Yeah. Yeah, sorry, I'm confused by that now. Let me. Yeah. Yeah. Okay. Paolo. No. I think Paolo had a question, perhaps.
Yeah, okay, sorry. A question maybe related to what Fabio was also asking during the talks of massive scalars.
Yes.
So I'm thinking about this because for massive scalars on Schwarzschild, there are quasi-normal modes which are low frequency. They can be low frequency depending on the mass of the scalar field. So I was wondering, can these symmetries play some role also for the spectrum of the quasi-normal modes in the massive scalar case?
Very good. I think that would be very interesting. I think one thing I'm working on right now is trying to develop a better framework to answer this type of questions, which is try to understand how to implement more systematically these near zone approximation, so that really you can answer questions such as, you know, how do the terms that we drop when I implement these near zone approximations compare to adding a mass term, right? Usually in any effective theory, like I said, there is a well-defined power counting parameter, and each operator is associated with some power of that parameter, and you can compare the size of your operators. And right now, we don't know how to compare the size of a mass type operator compared to the terms that we drop. And so I think that's the first step to then try to answer that question. Yeah.
Okay, I think we can thank Riccardo again.
Thank you.
Okay, maybe we should remind the speakers to send one of the organizers their slides. Okay.